We are going to start this deep dive with a little test. So I want you, the listener, to play along with us today. And, well, let's just see how my expert sitting across from me handles it too. Are you ready for a classic riddle?
I mean, always. Let's see what you've got.
Okay, so you are driving a bus. The bus starts with 5 people. At the first stop, 3 people get on.
Okay.
At the next stop, 2 people get off. Then 4 people get off. Finally, 5 people get on. So what is the bus driver's name?
Yeah, the groan-inducing answer is my own name or, the listener's name, depending on who is taking the test, because the very first thing you said was you were driving a bus.
Right, exactly. The trick always works on someone who hasn't heard it before.
Mm-hmm.
But the reason we were doing this isn't to test your riddle skills, obviously.
Thankfully.
Right. Unless you skip the math entirely. Your brain was actually doing something highly specific as I read those numbers out loud. You started with 5.
Right, and then I took that 5, added 3, and basically overwrote the old number to hold 8 in my head.
Yes, exactly.
Yeah.
And then you took the 8, subtracted 2, and overwrote it with 6.
Yeah.
You're constantly updating this single running tally.
Which is keeping a temporary value in active memory, and manipulating it step by step.
And that mental gymnastics is the exact foundational logic of how computers process information. Our mission for today's deep dive is to really demystify the logic of programming.
Right, using insights from a foundational text on scripting and programming we've been looking at.
We are going to look under the hood at how a machine actually stores, reads, and manipulates data. We're skipping the heavy jargon today, but we are absolutely getting into the mechanical reality of code.
Yeah, because that mental box where you just stored that changing number of bus passengers, well, that is the perfect representation of a variable.
A variable, right?
Yeah. In a program, a variable is just a named item used to hold a value. Human memory is incredibly associative and, fuzzy, but a computer's physical memory operates on strict, uncompromising rules.
Let's get into those rules, starting with what I actually like to call the great equal sign deception.
Oh, I like that.
Well, anyone who has taken a high school algebra class knows that if you see the equation x equals x plus 2, you are looking at a paradox.
Right. A number cannot equal itself plus 2.
Exactly. It violates the basic laws of mathematics. Yet in programming, x equals x plus 2 is like one of the most common lines of code you will ever encounter.
It really is.
So why did early language designers choose the equal sign if it behaves so completely differently from standard math? Doesn't that just confuse everyone?
Well, it comes down to early hardware constraints and just the evolution of language design. The equal sign in programming does not denote mathematical equality.
Right.
It represents an assignment statement. It is an action. It essentially tells the computer, hey, put the value on the right into the memory address labeled on the left.
Okay, so it's a command.
Exactly. Early languages, like Fortran, used the equal sign simply because it was readily available on standard keyboards. And the designers just needed a symbol to represent this transfer of data.
I always picture a variable as like a small physical whiteboard. Let's say I write num people on the top frame of the whiteboard.
Okay, I can see that.
When the bus starts, I write a 5 on the board. When 3 people get on, I don't write an 8 next to the 5. I take an eraser, completely obliterate the 5, and write down the 8.
Yes.
So in the computer's physical memory, that old state is just destroyed.
That destruction is key. Assignment statements rely entirely on sequential execution. The source text gives this really striking example using the spread of measles, actually.
Oh, right, the infection model.
Yeah. Imagine a program where the variable x tracks infected people. You initialize it with x equals 1.
So one person is patient 0.
Exactly. Then the program hits an assignment statement, x equals x times 20. The processor evaluates the right side of the equals sign first. It pulls the current value of x, which is 1, multiplies by 20, and holds that new value in a temporary register.
Just floating there for a millisecond.
Right. Then it takes that 20 and literally shoves it back into the memory address for x. It completely overwrites the 1.
So the whiteboard now just says 20. The 1 is gone.
Gone forever. Then the code runs that exact same sequence again. X equals x times 20. The processor pulls the 20, multiplies it by 20 to get 400, and assigns that 400 back into x. Yeah. In 3 quick steps, the variable jumps from 1 to 20 to 400. The previous states are entirely wiped from memory.
So once we have these cleanly defined memory slots or whiteboards, we obviously have to know how to label them. If the computer's that rigidly literal, I imagine we can't just slap a sticker on the whiteboard and call it a day.
Definitely not.
The text goes into identifiers,
Mhm.
which are the actual names programmers assign to variables.
Mm.
And the rules are ruthless, no spaces, no commas. They can only contain letters, numbers, and underscores, and they absolutely must start with a letter.
Yeah, and that rigidity comes from how a compiler physically reads your code. A compiler doesn't read a document the way you or I read a novel.
How does it read it then?
It uses a process called tokenization. It basically scans the text character by character to break it into meaningful chunks.
Yeah.
Spaces are delimiters. They tell the compiler where one instruction ends and another begins. If you put a space in your variable name, the compiler thinks you are listing two completely different commands, and it will panic.
It just throws its hands up.
Basically, yeah.
Well, I understand the restriction on spaces, sure, but why not just adopt the mathematical convention? Mathematicians just use single letters, A, B, C, X, Y. It's incredibly efficient to type.
It is efficient to type, definitely.
Or alternatively, if we need to be really descriptive, why not just write a massive run-on sentence without spaces so there is zero ambiguity?
Well, it is an ongoing battle between the machine's indifference and human cognitive load. I mean, the computer does not care if your variable is named X or average age of Euclid graduate student.
Right, to the machine it's all the same.
Exactly. But code is read by human beings far more often than it is written. If you use a single letter like a shift, the engineer reviewing your code 6 months later has no idea what that means.
Right, they're just guessing.
Yeah, they don't know if UFIS stands for altitude or apples or acceleration.
So brevity actually creates a nightmare for maintenance.
It really does. But on the other extreme, overly long names bloat the code. They make formulas completely unreadable on a standard monitor.
Right, you'd have to scroll for days.
Yeah. So the industry consensus is to find a self-describing middle ground. Something like num passengers is descriptive but still manageable.
You also have to navigate naming conventions, right? Because the compiler treats uppercase and lowercase letters as entirely different characters.
Oh, absolutely. It's based on their underlying ASCII values. So numcats with a lowercase n and numcats with a capital N are completely unrelated memory addresses to the computer.
The text mentions two main styles for dealing with this lack of spaces. You have lower camel case, where you squish the words together and capitalize the start of every new word, like the humps of a camel.
Right.
So people on bus has a capital O and a capital B.
Yeah. And the alternative is underscore separation, which is also known as snake case. Like people underscore on underscore bus.
Okay, snake case. I like that.
Both serve the exact same function. They trick the compiler into seeing a single token while allowing human eyes to see separate words. You just have to be careful not to accidentally use a reserved word.
Reserved words, these are the words the programming language claims for its own grammar, right? Like if, while, or integer.
Exactly. If you try to name your variable integer, the compiler throws an error because it thinks you are issuing a structural command, not naming a memory slot.
So it's waiting for an instruction.
Yes. The language's parser hits that token and expects a specific grammatical structure to follow. When it just sees an equal sign instead, the compilation process halts.
So we have these memory slots cleanly labeled, and we know we have to respect the compiler's tokenization rules. But variables are kind of useless unless they interact,
Right. We need the processor to actually do something with them.
which is where arithmetic expressions come in. The source text gives an example of calculating a user's age in minutes and estimating total lifetime heartbeats by combining variables, literal numbers, and operators.
Yeah, and it is straightforward when you are just multiplying age in years by 365 days. The complexity scales up quickly when you introduce real-world formulas.
Oh, totally. The text actually includes this massive formula for calculating calorie expenditure during exercise.
Oh, right, that one.
It involves multiplying age by decimal, subtracting weight multiplied by another decimal, adding heart rate factored by yet another decimal, and dividing the whole thing by time.
It's a lot.
It is a lot. When I look at a string of operators that long, my question is, how does the compiler not just blindly read it left to right and produce a completely garbled result?
Well, it doesn't read left to right because the compiler doesn't execute text. It builds a data structure.
Okay.
It uses precedence rules, which is the programming equivalent of mathematical order of operations, to construct what is called an abstract syntax tree, or an AST.
Abstract syntax tree. Okay, how does that actually work in practice?
Well, when the compiler parses your expression, it looks for the highest precedence operators first. Parentheses are at the very top. Then comes the unary minus.
And just to clarify for everyone, unary minus is when you negate a single value, like writing negative x, as opposed to subtracting one value from another.
Yes, exactly. The negation applies directly to the variable before any other math occurs.
Right.
After unary minus, multiplication and division are processed, followed finally by addition and subtraction. The compiler uses these rules to build a tree structure from the bottom up.
So it's like a physical map of the math.
Yes. The branches of the tree dictate exactly which operations feed into the next ones, ensuring the final evaluated value is mathematically sound, regardless of how the text was ordered left to right on the screen.
But if the compiler is so smart at building this tree using standard precedence rules, why does the text heavily advise programmers to use parentheses even when they aren't strictly necessary? Because if I write x plus 1 times y divided by 2, the compiler knows to multiply and divide before adding x.
It does. But human memory is faulty and debugging is incredibly expensive. Even if the AST builds correctly, the next programmer to read that line might second-guess the precedence.
They might not trust the computer or themselves.
Exactly. By writing x plus, open parenthesis, 1 times y, close parenthesis, divided by 2, you are explicitly defining the shape of the syntax tree for the human reader. It removes all ambiguity.
It's like adding an Oxford comma in a sentence.
That is a great comparison.
The machine might parse it fine either way, but you are saving your coworkers a massive headache. And speaking of human readability, the text notes that spacing around operators doesn't change the abstract syntax tree at all.
Right.
So writing x plus y squished together versus x base plus space y, it's identical to the computer.
Yeah.
The spaces are purely aesthetic for our benefit.
The compiler just strips out that extra white space during the tokenization phase we talked about earlier. To the machine, it's completely irrelevant.
Now, we all know what whole numbers and decimals are from basic math, but the text makes a huge point about how computers treat them as entirely different species. Integers versus floating point numbers.
Yes.
Why does the computer care? I mean, a number is a number to us.
To us, yes, but not to a microchip. The difference really lies in the physical hardware architecture of the computer itself.
Oh, so.
While modern CPUs have different physical pathways for processing numbers, they have an arithmetic logic unit, or ALU, optimized for handling fast integer math. And then they have a floating point unit, or FPU, designed specifically for the complex binary representation of decimals.
The functional distinction seems to really be counting versus measuring.
Yes, exactly.
Like integers are for things you count 42 cars or 10 pizzas. You can't have 42.4 cars.
Right, unless things have gone horribly wrong.
Exactly. Floats are for things you measure, where the decimal point can basically float anywhere, like a temperature of 98.6 degrees or a distance of 400.5 miles.
That conceptual distinction maps perfectly to how we actually use them. But the physical constraints of memory are where things get dangerous.
Dangerous how?
Because integers are stored in a fixed amount of memory, typically 32 bits in standard programs, so they have a hard cap. A 32-bit integer can only hold a value up to about positive 2.1 billion.
I have to pause you right there. Memory is incredibly cheap now. My laptop has 32 gigabytes of RAM. Why in the world are we still capping numbers at 2 billion like it's 1995?
It is entirely about processing efficiency. The CPU is designed to pull data in highly predictable, standardized chunks.
Okay.
If variables could be any random size, the processor would waste enormous amounts of time just trying to figure out where a number starts and ends in memory.
Oh, that makes sense.
Right. By locking integers into 32-bit or 64-bit blocks, the hardware can execute billions of operations a second flawlessly. But if you try to stuff a number larger than 2.1 billion into a standard 32-bit integer, it causes an overflow.
Wait, it doesn't just lop off the extra digits?
No. It usually wraps around to a massive negative number or causes the system to crash entirely.
Yikes.
Yeah. And this isn't just a theoretical nuisance. One of the most famous software disasters in history, the explosion of the Ariane 5 rocket in 1996, was caused by a number conversion error.
Wait, really? A rocket blew up because of this?
Yes. The software tried to stuff a 64-bit floating point number representing the rocket's velocity into a 16-bit integer space.
Oh, no.
The resulting overflow caused a complete loss of guidance, and the rocket self-destructed 37 seconds after launch.
That is a staggering consequence for picking the wrong variable type.
Yeah.
It really makes the text's warning about using floats for money seem incredibly urgent.
Oh, absolutely. Money is a fascinating edge case. On the surface, money looks like a float. $14.53 is written as 14.53.
Right.
But financial institutions rarely use floating point numbers to store balances.
Because money is actually countable, like you can count physical pennies.
More importantly, it's because floating point numbers are stored in base 2 binary, which cannot perfectly represent certain base 10 decimals.
What do you mean?
Well, in the same way that 1 divided by 3 creates a repeating fraction in decimal formatting, no, 0.333 forever,
Right.
decimals like 0.1 become repeating fractions in binary.
So the computer physically cannot store an exact representation of 10 cents using a float.
It stores a microscopic approximation. If you do enough math with those approximations in a banking app, those fractional rounding errors compound. Suddenly, actual money disappears from the ledger.
That's terrifying for a bank.
Exactly. So to avoid this, programmers just use integers to represent the total number of cents. $14.53 becomes an integer of 1,453 cents.
They just bypass the floating point hardware entirely to guarantee absolute precision. I love seeing how human logic adapts to those hardware limitations.
Me too.
Another quirk of those limitations happens when you try to break the oldest rule in math, dividing by 0.
Oh, yeah. The outcome again depends entirely on the hardware pathway you are using.
How so?
If you instruct the ALU to divide an integer by 0, the hardware literally doesn't know how to complete the operation. It triggers a hardware exception, a fault, and the program usually crashes immediately.
The processor essentially just throws a fatal error and walks away.
But floating point math operates under a specific international standard known as IEEE 754. If you divide a positive float by 0, the FPU doesn't crash. It returns a special designated value called infinity.
And if it's a negative float?
It returns negative infinity.
Right, and what if I tried to divide 0 by 0 using floats? Like
Yeah.
0.0 divided by 0.0.
The FPU outputs another special value, NaN, which stands for not a number. It is the system's way of gracefully handling an undefined operation without taking down the entire program.
NaN. Not my problem. Keep running.
Pretty much.
It's brilliant. We've covered operators and data types, but programming languages don't force you to build absolutely everything from scratch, do they? They come with built-in functions.
Yes.
Things like square root, raised to power, or random number.
Right. Functions are basically prepackaged blocks of code designed to perform a specific task. You trigger them with a function call, and you hand over data inside the parentheses, which are known as arguments.
You know, I used to think of functions as black boxes. But based on how we've been talking about memory and processors, I actually see it more like hiring a subcontractor.
Oh, that works much better because it emphasizes the handoff of data.
Yeah. If I need a square root calculated, I don't need to know the complex algorithm to find it. I just call the square root subcontractor. I hand them the argument, say the float 49.0.
Right.
They go off, do their specialized work, and hand me back the evaluated result, which is 7.0.
Exactly. You provide the inputs in the required format, and you just trust the output. If you call raised to power, you hand the subcontractor two materials, a base and an exponent, separated by a comma.
So you pass it 6.0 and 2.0, and it hands back 36.0.
Yes.
The true power of this system, though, really becomes apparent when you start nesting these functions, passing the result of one subcontractor directly to another.
Using a function call as the argument for another function call.
Right. The text gives an example of an algebraic model formatted as raised to power, open parenthesis, 2.0, comma, raised to power, open parenthesis, x, comma, y, close parenthesis, plus 1, close parenthesis.
Right. And the compiler syntax tree handles this from the inside out.
Always from the inside out.
Yes, it evaluates the inner function first. The raised to power subcontractor takes x and y, calculates the result. Let's just say it evaluates to 9.0, and then it adds the 1.
Okay.
Now, that combined 10.0 is handed off as the argument for the outer function, evaluating 2.0 to the power of 10.0.
Which produces 1024.0.
Exactly.
By nesting these specialized subcontractors, you can translate immensely complex models like biological mass growth algorithms or planetary orbital physics into incredibly clean, solvable architecture.
It abstracts the complexity, allowing the programmer to focus on the overarching logic of the software rather than manually calculating the math at every single step.
Let's bring all this mechanics back to you, the listener. What we've seen today is that programming is far less about being a math genius and far more about understanding a highly literal, physical system.
It really requires learning to manage memory through variables, understanding how a compiler parses identifiers and builds syntax trees, and respecting the physical hardware limits that separate integers from floats.
We started with the mental exercise of keeping a running tally of people on a bus. A computer is simply doing that exact same process, obliterating the old whiteboard value to store the new one, just billions of times a second without ever losing track.
It's pretty amazing when you think about it.
It is. I want to leave you with a thought experiment that applies this rigid machine logic to our daily lives.
Let's hear it.
Think about the arguments or miscommunications you have with colleagues or family members. How many of those conflicts happen because one person in the conversation is operating with a floating point mindset? Right. Seeing an issue as a spectrum, a measurable gradient of gray, while the other person is using an integer mindset, basically treating the issue as discrete, countable, black and white.
The hardware analogy applies beautifully there. You literally have two people processing the exact same information through completely different logical pathways.
If we define the terms and variables in our human conversations as strictly as a compiler forces us to define them in code, would our communication be more flawless? Or would our relationships just throw a fatal hardware exception and crash?
A syntax error in human dialogue. That is an incredibly insightful way to frame interpersonal conflict.
Something for you to mull over until next time. Think about whether you are arguing with an integer or a float, and we will catch you on the next deep dive.